experiment 4, we'll be looking at the reaction between iron 3 ions and thiocyanate ions to produce a thiocyanato-iron 3 complex. Because this complex is orange-red, its concentration can be monitored using spectrophotometry. The first stock solution we'll be using is 1.00 times 10 to the negative 3 molar potassium thiocyanate. The second is 0.200 molar iron 3 nitrate. And the last one is 0.50 molar nitric acid, which is going to be our solvent for this experiment. Notice that the other two stock solutions are prepared in 0.50 molar nitric acid instead of water. Nitric acid is being used here to suppress a side reaction that happens when iron 3 ions hydrolyze in water to form this yellow-orange complex shown on the bottom of the screen. Nitric acid is a strong acid and a source of hydronium ions. As you know from Le Chatelier's principle, if you disturb a reaction that is at equilibrium by increasing the concentration of products, in this case hydronium, it will cause equilibrium to shift to the left, thereby suppressing the formation of this yellow-orange complex. In part 1, we'll be preparing 5 standard solutions of our thiocyanato-iron 3 complex in order to make a Beer-Lambert plot. This table can be found in your lab procedure, and it tells you what volume of each stock solution to add to each flask. Notice that the total volume is the same for each run, and also that the concentration of iron 3 stock solution is much higher than that of the thiocyanate. Since we're adding a large excess of iron 3, this reaction is getting driven to near completion, and we can treat thiocyanate as our limiting reactant when calculating the concentration of our thiocyanato-iron 3 complex. Because we're using so many different volumes, it's convenient to have each stock solution in a burette for dispensing the volumes that we're going to need. Your instructor will provide you with a video showing you how to properly prepare a burette for use. But in the meantime, let's look at what not to do. While watching this video, write down as many mistakes as you can find. Afterwards, we'll review. All right, let's look at some of the things that went wrong in that last part. Just like when you're preparing a pipette, you want to condition your burette with the solution you're using a few times after rinsing with water. Let it drain through the tip so that part also gets rinsed out. Make sure the stopcock is closed before filling the burette so that it doesn't spill. Check that the burette is straight and lower it down so you can easily pour the solution in without having to reach too far overhead. Be sure to remove the funnel when you're done filling. If you leave it there, it can drip and affect the volume reading. Before you get started, you want to check the tip to see if there's a bubble there and remove it if there is one. They're hard to see sometimes when your solution is colorless, so I've outlined it here in red. One way to remove a bubble is to open the stopcock and very quickly give the burette a shake over a waste container. Always leave your goggles on, even when you're reading the volume from the burette. It's really important for the accuracy of your volume reading that the meniscus be at eye level. So if you have to raise the burette or lower it down, go ahead and do that. You can also use a meniscus reader, which is just a card that has a black line on it to help you read it more accurately. So we would prepare 3 burettes this way, one for each of our stock solutions: the potassium thiocyanate solution, the iron 3 nitrate solution, and also our 0.50 molar nitric acid solution. It's important to label all of them so that they don't get mixed up. So now we're ready to prepare our 5 standard solutions. I like to add one solution at a time so I don't get mixed up. So first I'm going to add the volume of potassium thiocyanate solution that I need to each flask. Next, I'm going to add the volume of iron 3 nitrate solution that I need to each flask. You're going to see that the formation of that thiocyanatoiron 3 complex causes our solutions to turn sort of orange or red-orange. Lastly, we're just going to top off each solution with our 0.50 molar nitric acid solvent, just to make sure that the overall volume of each standard solution is the same. So as you can see, we've prepared 5 solutions of thiocyanatoiron 3 in decreasing concentration, going from solution number 1 to solution number 5. So now we're ready to take the absorbance of each solution. We're going to use nitric acid to calibrate the spectrophos this time, since that's our solvent. Fill a cuvette about 3/4 of the way full with nitric acid. Click on the red box and choose Calibrate. I'm going to speed up the calibration process while I wait for the lamp to warm up. In the meantime, I'm just putting each standard solution in a cuvette. When done, you can press Finish Calibration. And then click on OK. So now we're ready to take the absorbance of solution number 1. I'm going to press the play button. Once you see the spectrum, you can click on Stop. Double click to get this rainbow out of the way so you can see the peak better. The peak needs to be manually selected. As you can see, our lambda max is in the blue region of the spectrum, which you would expect for an orange solution. The wavelength is 449.20 nanometers. On the y-axis, you can see that the absorbance at this peak is 0.467. You can go ahead and write that down in your lab notebook as the absorbance of solution number 1. Before measuring the absorbance of solution number 2, I'm going to put this in Events with Entry mode to make it easier. Click on Mode and click Events with Entry from the drop-down menu. Double check to make sure that the wavelength mentioned is our lambda max. This is the absorbance at that peak for solution number 2, so go ahead and write that down in your notebook. This is solution number 3. Solution number 4. And lastly, we're going to measure the absorbance of solution number 5. Part 2 involves an equilibrium reaction, we have to start by diluting our stock solutions so that the concentration of iron 3 and thiocyanate are more similar to one another and that they will reach equilibrium when they react. First of all, I'm going to prepare a 2 times 10 to the negative 4 molar solution of thiocyanate by dispensing 20 milliliters of our stock solution into this 100 milliliter volumetric flask. Next, I'm going to dilute this solution using the 0.50 molar nitric acid stock solution. Remember that when you're preparing a solution, you don't want to fill it all the way up to the mark at first. You only want to fill it about halfway to leave room for mixing. Mix your solution thoroughly. Then you can carefully dilute it to the mark. When you get close to the calibration mark, use a barrel pipette to add the solution drop by drop so that you don't accidentally overshoot the calibration mark. The meniscus of your solution should be sitting right on the calibration line. Once you're done, you want to continue to mix thoroughly by inverting several times. Next, we want to prepare 20 milliliters of 0.100 molar iron 3 solution. To do this, we're going to add 10 milliliters of our stock solution to this flask. And then on top of that, we're going to add 10 milliliters of our 0.50 molar nitric acid. Dispense 10 milliliters of the iron 3 plus stock solution from the Buret. And then continue by dispensing 10 milliliters of the nitric acid stock solution to the flask. When done, we're going to pour our entire thiocyanate solution into this beaker to make it easier to perform our reaction. So what we'll be doing is pipetting 1 milliliter of our iron 3 solution we just prepared into the thiocyanate solution, place it into a cuvette, measure the absorbance, and then dump it back in. 1 more milliliter, measure the absorbance, dump it back in. We'll do that until we've added a total of 5 milliliters of this iron 3 solution to our thiocyanate solution. Remember that you just want to let a pipette drain naturally without forcing it. You're going to see the solution start to turn orange. This is due to the formation of our thiocyanate iron 3 complex. Swirl it to mix. Now I'll be filling a cuvette about 3/4 full to measure our absorbance at the same wavelength as our standard solutions. Go ahead and write this down in your lab notebook as the absorbance of solution number 6. I'll be pouring this back into our beaker containing our reaction mixture. And now I'm going to pipette 1 more milliliter of our iron 3 solution into our reaction mixture. Swirl to mix it up. You may be noticing that it's getting slightly darker each time we add iron 3. Go ahead and write this down as the absorbance of solution number 7. 1 more milliliter of the iron 3. I'm pouring the solution back. You can write this down as the absorbance of solution number 8. Pour the solution from the cuvette back into the reaction mixture, and we're going to pipette 1 more milliliter of the iron 3 into our reaction mixture. This will be solution number 9. Pour it back in. And then the last one, we're going to pipette 1 last milliliter of iron 3 into our reaction mixture. This will be solution number 10. Go ahead and write down this last absorbance in your notebook. And that's it. So you'll be using the Beer-Lambert plot from part 1 and the absorbances you measured for each solution in part 2 to calculate what the equilibrium constant is for this reaction.